Actually, I'm thinking about going and applying to do the thing online because actually, I think I could do a better job. It's been, I don't know.
Well, then you can record at a time when you feel, you know, awake and good.
Yeah. Well, also, I could focus specifically on a topic and then, you know, do that for a problem, do that for a problem, just go through it one at a time. It may actually be better that way. I don't know. Some people are resistant to it. I guess I've been too much so. Uh, so maybe I need to be a little less resistant to it. Okay, let's see. I didn't mean to open that. I need to open that. And now I go to there, not there, not there. Yes, there. Oh, I didn't get all there. Yeah, if you think about it, you actually could make a really good course that way. That's kind of the new. There's some courses you could do that way. Some courses, you can't really do a lab that way. And you could try to, but yeah, I know. I guess my let's see, maybe it's got that. Ah, there we go. All right. Oh, they changed the way they did some of this. That's not the button. Well, no, I could go with that button. So I'll get into curve gate once I get in there. Actually, I guess I could just go straight. Let me just go straight and do a curve gate for my drawing. Just draw my own words. There. So curve gates are weird because they're curved. But the most common is a curve that is a circle. I'm trying to do a decent job here. Let's say you had a gate that was like this. Somehow it was sat on a concrete hinge right here, and then you got water back here. So 62.4 pounds per cubic foot. And say this is a curve gate that's actually a circle, quarter circle, I mean, and not a really good drawing, but it has like a, that is not, maybe I need to tell you what, do this, put it that way, see, notice that, there we go. So it kind of has a radius all around of, say, make something up, 10's a good even for 10-foot radius. And then say it's 5 foot in the page. And then the question, is this going to break off, or what is going to be the force here that's going to be pushing on that? And it's kind of a strange way you approach this. But I think what I'll do is do the free body diagram over to the side and hope that it looks kind of like a circle. Okay, so you got a hinge force up here. I can just say, oops, we can put the H first. Hinge X and the hinge Y. So obviously the best thing to do is sum the moments about the hinge, but you got to know all the forces that the water puts on the gate. To be kind of detailed, I'm going to kind of try to be detailed for a minute, and then I'm going to go back to a generalization. And so up here you have pressures equal to 0 because it's at the top. And then down here you have the pressure is equal to R times gamma because that's the radius all the way down. And then up to a certain point, you know, depending on the way you sweep this thing, you could sweep it from this point up or not. But then the pressure at, say, this point becomes gamma times the height, which now becomes cosine theta. Now, the thing is not only that, but you have a situation in which, okay, this is ugly, really ugly looking. The force produced by the little d area, or say the d force, has a component that goes to the right and a component goes down. So, you know, there's a d area there. So there's a pressure value, which is that, the d area, but the d area, you'll end up with a value going this way and a value going that way. Really, what you do is integrate the whole thing. If you want to see that done, you just want to kind of, I want to say, torture yourself or whatever. Go in here to the videos and see curve gates. Really slow. I think, hang on. So this is a situation. I went and did this through here. Maybe it's not the most efficient table. So think of it as a proof. So this is not the most efficient way to do it. But if you look at that, so 30 minutes, and I don't want to take 30 minutes, but if you look at this, you can see that, oh, here, maybe make it full screen. That may be a problem in and of itself. Oh boy, I don't know if I broke something. So what I did is I did this at one point. Looks to me like I took the theta from the top. And I worked the whole problem out. So if you want to see a way to do that, that's great. But what you'll find out is the answer you get is the same way as projection. And I'll do the problem that way in a minute. So there's the whole thing integrated out for your enjoyment. And the end result, I think it's somewhere near the end result. Yeah, I think I worked it the other way to the end result. So let's look at how you would approach this in general, but not integrated. So we don't want to do that, but there is I do have a proof. Make sure I stop that. Yeah, because I don't know if I'd chew up my bandwidth. So we don't want to do that, but you can look back if you really want to see it done that way. That's a great idea for you. But here's another way of thinking about this. Let's imagine for a second that we took some sort of freeze ray and we froze this block that's just this. It's just this part right here. And it had a centroid, but it was what they call neutrally buoyant. So in other words, here's what I mean. So if gamma's over here at 62.4, and you froze this block and say it was 62.3, it would start floating up a little bit. But that's not what we've got. We got 62.4. So it's exactly the weight of the stuff back here. So it has a weight associated with it. And let's say we froze it to the degree that it bound itself to the gate. So it's almost like welded to the gate now. So it's part of the gate. It's welded there, and it's got a weight associated with it. Okay, so give me a second here. The weight is equal to the gamma times the volume of it, and the volume of this is pi r squared. That would be if it was a complete circle, but it's a fourth of a circle because actually you got the other parts there. And then it's times the d, which is the depth into the page. So that is the volume of the thing. And I don't want this to become confused in the time, so I'm just going to do that. Pi, this is the area of the projection. That's the depth into the page. So that's the weight of the thing. Thing is, we've got to find the right location, which that'll be the centroid of this thing. And so we'll figure that out. But just imagine it got glued to this gate through, we froze it and it froze to the gate. So now it's part of the gate. And so now to the left of the gate, we've got this force on. So we've got a force pushing to this thing that was now glued to the gate and became part of the gate. And that's all the forces we got. So let's see if we can work through this and figure this out. So if we slide this over like this, what we need to do is find the centroid of half circle. I think it's 4r over 3 pi, something like that. But let's double check that because my memory sometimes fades and disappears. So let's just find that. There, centroid of a quarter circle. Okay, centroid of a quarter. I don't know that I really necessarily how to want to find it. In so much as list of centroids. Let's just do that. Because then there'll be other ones. I don't think we need another one in this, but just in case. So there it is. Quarter circle. And one of them, say the one of them's going to be X, one of them's going to be Y. The first one is the X right here. And then the second one is the Y. So the first column is X, second column Y. But what's interesting is they're both the same. 4r over 3 pi. Of course, there's your area of it. And we knew that before. But I just wanted to double check. 4r over 3 pi is the distance from here to here. So I don't know anything to do except just say 4r over 3 pi. So now this part right here is a triangular lobe. So here's what I'm going to try to do. I will try to do this. And I'll just do the best I can about copying this. And I'll just put it right here. But this time, I'm going to be a little bit more. I'm going to take this triangular lobe and turn it into a point lobe. So what is the value of that triangular lobe? Well, it's the depth. Pressure at the bottom. So here you go. Pressure at the bottom was equal to the radius. What did I say the radius was? 10. So the radius times gamma, or 10 times 62.4, or 624 pounds per foot squared. Now, it's applied over a area of 5 by 10 feet. So, so the pressure applied over that particular area is 624 5 by 10, and this will be feet squared, and this is pounds per square feet. But half of it is missing. In other words, that's a very terrible. Here, I'll do it like this. So this is the part of the missing area here. So you got to drop it down by 2. And so this becomes Okay, did I have this up before? Where? There it is. Give it a second for this to come up. Okay. 624 times 5 times 10 divided by 2, 15,600. That it comes out in pounds. Whoops. And it's a third up. Now, I should have made that 9, but that's okay. So in other words, the radius is still 10. So this distance is 10 over 3. And this value is 15,600. Now, this value is, okay, 40 over 3 pi. That's the distance between here and here. The value of this load becomes 62, I'm grabbing those values, 0.4 times the pi times the radius squared over 4 times the distance into the page. I think the way I'll do this, I think I'll just produce that number. Well, you know what? Let's see. Just out of curiosity, can it read off of my laptop? I guess it can. Hmm? That's a pretty large number. I'm kind of doubtful, but he says 7,800 times pi. I'll leave it like that for the moment. Yeah, I guess that could be. And so now I'm basically have enough information to sum the moments about that hinge point. So I don't have to include those forces because they're out of the way. So, let's see. So what I'll end up with is, I guess I got to pick a positive direction. So I'll pick that. So now the F goes this way. So I'll start with it. Minus F. Moment arm out to the F. Here's your F, and there's your moment arm. That's 10. Then I don't know which one to do next. We'll do this one. It goes this way. And it is in a positive direction. 15,600 times, this is the distance to the moment arm. And that's 2/3 times 10. This is actually 2/3. Oops. 10 times 2/3. And that gets that. And then you got this one providing a moment that way, which is positive as well. 7,800 pi. And its moment arm is 10 minus 40 over 3 pi. So if I wanted to find the force, I could take this and move it to the other side, and the force would be equal to, okay, let me just, okay, first of all, I'll take the 10, put underneath, then I'll have 15,600 times 2/3 times 10 plus 7,800 pi times 10 minus 40 over 3 pi. I have no idea what this is going to be. And this is only it. Let's see if it can figure it out. Let me make sure I've got the right thing. Oh, man. Am I seeing that right? It says the thing is 7,800 pi. Let me make sure I've got it's copying all those things. So there's your force. Now, this is a bizarre thing, but there's something even more bizarre about this in a second. Okay, make sure I've got over 10. I think it's solved it out correctly. Okay, so here's something bizarre about a curved gate. And what I'll do is I guess I'll just copy this same picture. Don't know what's the best way to do that. I guess I could just maybe let's see, can I work off the same picture? Tell you what I'll do. I'll just try my best to copy as much of this as I can without too much. And I'll put it close at hand so I can look up and grab the numbers. Okay, now there's a lot of extra dirt around it, so let's see. Okay. So what I'm going to do now is really weird. And I'm going to pick this spot O right here. And I'm going to do something very strange here. And what I'm going to do is I'm going to ignore, well, I'm trying to think if I want to say that I'm going to ignore those forces or I'm going to reform things. I guess I'll reform the problem. So here's the new problem. Problem is you've got the hinge back here. You got a big metal piece. Doesn't have to be metal, but it probably should be. Comes out to here. Somebody welded it onto this. Another big metal piece came down here, welded onto this, and this is the arc of the gate. That doesn't look like an arc, but you know, so this and this are the same. The gate is just not being held by a hinge here and pushed up. It's just the supplying forces, basically this metal rod and that welded to this curved gate. So essentially the free body diagram looks like this now. And I don't know, oh, what happened here? What happened to my pins? Oh, there they are. So I have a hinge force here and a hinge force back here. So it's obvious that at this point you want to sum at the moments about the hinge point. So I'll just call it H. And there's something that bizarrely comes out of this. Now, here's the deal. Let's say the gate weighs nothing, and you're going to try to open it by pulling it with some force P there. Or maybe I better use a different R or something. So you're going to pull this thing with R. So the gate weighs nothing. It's somehow some mystical something. Or maybe what you got is you got the thing with the counterweight out here so that it just balances perfectly. And then you put water behind it. And as you put water behind it, does the water make the gate open or close? Is this going to have to be a value to keep it closed? So the ground comes up like this. Maybe there's a few leaking out of there, but not much. And so the question is, what's that going to have to be to keep it closed or to open the thing? Given the fact that its weight is centered right there. So at some moments about the hinge, the only two forces you got now are from the water. It's that one and this one. And so let me monkey with those. I mean, I guess I'll do the, here, I'll do it this. Oops. Let's do this being positive. And we'll go ahead and put the R force in there. So 10, because that's the distance from here to here. And times R And then this force goes this way. And so it is a minus. Okay, what was that weight? That weight was 7800 pi. 7800 pi. That is this value, 7800 pi. And its moment arm is 40 over 3 pi. It's just this. And then you got this 15,000, which is going in the positive direction. That. So it's going in the positive direction. 15,600. And its moment arm is that. Is 10. Why did I write pi? 10 times 2/3. So now if you carry this out, let's see, 10r plus, minus. Okay, so the pi's will cancel. So I'll get 7800 times 40 over 3. And then what I'll get here is 15,600. And I can put that up there is 20. Right here, I'll just do it like that. 20 over 3. Now if I do let's just do this. 7800 times 40. 312,000 over 3 plus 15,600 times 20 is 312,000 over 3. That one had a minus, so 10r, and this had to equal 0. So that tells you that r is equal to 0. And in fact, that's really why you go out to the Darnell gates out there, and they're all made like arcs or quarter circles. They don't even have to be quarter, they can be larger than quarters. I don't know that I can get a picture of that. Let's see. Oh, it was already there. Okay. Somebody's got to have a picture out there. Well, I say that. They have a Facebook site. I don't know. It's all great. That's not what I'm looking for. I want a picture of the. I tell you what, this might be better. Sometimes people will put their pictures on the thing. If you can go out there. Hello. Hello, computer. Hello, computer. Computer. Oh my God. Now, does it have? It does have. I wonder if it would come up under pictures of that. 7 photos. There's a playland there. There you go. Maybe that's the best I can find. Looks like that's going to be the best I can find. So, oh, it went away. Okay. Okay. There it gets that too. So I guess you can kind of see the arc on them. And the water's being pushed back the other way, but it really doesn't matter. So it doesn't matter whether the water's on the left side or the right side. So in fact, if you balance these, I don't think they're balanced, but I don't know. But if you were able to balance this before water and you started putting water in here, the water itself is not going to push it open as long as that's a circle. If it's something beside the circle, like an ellipse or something, it could actually push it open. But anything besides a circle won't. And the reason being is because as you fill it up, say it's not completely full. Oh man, this is weird. Imagine that's a circle, quarter circle. So let's say you fill it up to there. Then actually, okay, so let's say the water level is right there. Then say right down here, the pressure's like that. A little deeper, the pressure's higher. A little deeper, the pressure's higher. But all the moments, the forces are acting through that hinge, if that's a circle. So as you fill it up, nothing's happening. It doesn't happen. I mean, I guess if you pull it over the top, it'd roll over the gate, but that really doesn't matter. So the thing is great because, and of course, it doesn't matter whether you're on the left side or the right side. In other words, if you're on the far side filling it up, the same thing applies. You can fill the water to right here, pressure 0 here. All the pressure values, you get more when you go down. They're the largest at the bottom, but all of them the forces are going right through the hinge point there. So, and if you had a big heavy gate, say you had a real heavy one, you could you got to weld it to the hinge somehow, so it's got to be welded. You could actually have a rod out here with a little, say this little part could be moved to the left or right. If you move it too far one way, the gate will tend to go that way until it rebalances itself. And you move the weight the other way. So if you move the weight way further out, it's going to start tipping up that way. So you're going to actually make it so some guy could come in here with a hammer and beat on the weight and make it move that way, and then the gate would open. Sounds like a weird thing to do, but they don't do that. I mean, they have a motorized method of doing it. So curved gates have that effect to them. And so let me dart down back to that. Yeah. Okay. Go down to, I was not in, hit the wrong thing. Content. Go to the book, which I thought I opened. Oh, maybe I did. Did I? Yeah, I did. Okay, so he has a section. Let's see if I can find that section. Okay. Okay, he says by projection, buoyancy. Okay. Can't touch that. Yeah, let's see what his little description combining these two can be a little confusing. So I'm not sure it's the best way to do it. I was going to do, and I started looking at how to do this in CAD, and it does work, but it'll take me a little time to put that together. But he does this where, your force is actually dictated by your area, your force direction. And he goes through this. There's part of me that kind of feels like this is an overcomplication of this, but I don't know exactly. Doing this way. This sometimes confuses people. Okay. So look at that if you want. Very slow response time. But the other way of approaching it is the way I've been talking about. It's like a pseudo area. It's basically, let's look at it we got enough time to do the reverse of this, and that is what would happen, how would you mentally approach it if the water was on the other side of the gate. So here I'll draw a circular gate. And so here it is. The water's on this back side. Okay, so let me do it like this so that we have the gate, and we're make it a little less complicated. So how do we find, let's say this is our F. How do we find the water force on this gate? And there's two ways to look at it. One is you stand back here. This is the simplest way, I think. You stand back here and a person here sees a flat gate. So in this is what the person sees. It is height is the same as the radius back here. So let's just do this. Radius equal to 10. He sees that. But then their water is pushing back up on it. But let's imagine for a minute, here, radius equal to 10. Let's imagine for a minute we did something similar that we did last time. We took some substance and we froze it to the gate. We welded it to it. But this substance is a solid, and its centroid is right here. We're going to take the same thing. Depth is equal to 5. So you've got two forces here. You got the horizontal and the vertical. This time the vertical operates, the horizontal operates that way. Last time, it's the same dimensions. Everything is the same. It's just that this force, it's flipped the exact opposite direction. And so that's going to be equivalent to that 7,800 pi. This is going to be equivalent to, what was it? 15,000? No, I'm sorry. That was the 7,800 pi. This was the 7,800 pi, and this was the, what was it? The 15,000. Yeah, 15,600. 15,600 right here. So it's the 15,600. Now, here's the deal. Okay, you took this object here and you welded it, and suddenly you got the thing balanced. So you got a water force pushing back up at 7,800 pi. If you erased it, it would be flipping that force over. So this is what some books will call a pseudo volume, and you'll actually see them use that term. And what it is if you find out what that value is, that volume, the actual force goes the other direction. And so some textbooks will write it like that and just put it up there and just flip its direction. So gravity goes that way. You somehow just make it disappear. It goes the other direction. So if you want to, you've got the same distance here, 4r over 3 pi. This it's still 10, so it's 10 over 3, the distance there, or 10 times 2/3, the distance up here. You got your 15,000. You can do a variety of things. One is, if you hinged it here, say you need to know the force here to hold it back. You sum the moments about the hinge. Say that's the force, it's still 10. And so that would be, that being positive would be minus F because it's going in the other direction, times 10 because that's the moment arm, plus, and that's a plus because this is going this way, 7,800 pi times the moment arm of that 4r, which is 10 over 3 pi. And then you got this last force right down here, which is going this way about the hinge, which is minus 15,600. And the moment arm is 10/3. So with that, you could find the force there. You could also come in and say you've got, like the Lake Darnell, you've got this, and you've got a hinge force right here. So if you did that, we'll move this out of the way. If you got that one, you got a slightly different situation. And you sum the moments about that hinge equals 0 equals 2, and guess what? You get, let's see, make that positive. So this would be negative minus 7,800 pi times 4r over 3 pi. And then this would go, oh wait, that one's going that way. If that's positive, I goofed that up. This is going the negative way. So this is going to 15,600 times the moment arm from there to there is 2/3 of 10. And guess what? That equation is exactly the same as, so if you stare at this, these two terms are the same two terms right there. And so these will both end up being that, 312. But what happened is the signs changed here to here. So the key is mentally, what do you do if you've got, say you've got some object like this, in which you have air back here, and say the water is sitting here, and say the gate, and I think this is one of the cases I did in that one of the videos. So this is all water, and it's pushing back here. Well, it's as if this bubble, it's wanting it to float. So the water is trying to push this gate up, but it's also trying to push it back to the left. So if you ever want to see that, just go out and take a gas or something, or some sort of container, push it down in the water, and you'll see the water is pushing on it here, pushing on it here. It is pushing on it here, but what's the part that's making it go up is this part. The fact that you have to push it down in the water, it'll try to rotate that thing up. So I don't know if that's clear, but I can do more on it, and probably did better on the videos. I'm pretty sure I did better on the videos that I'm doing right now. So, okay, yeah, so I would not hesitate to, okay, my brain, there it is. These videos are better than what I'm doing right now. So if you go into the curved gates, I would say go watch these. There I do one with 2 weights. And here I do one where there is 1. And then there's that proof. So if you want to be just entertained, you can do that. What you'll find out is that proof will show you that this mentality works fine. And I'll tell you this much, this might be very difficult for some people. So I remember when I taught at another university, there became a very interesting argument about a planar face, that actually if you went through the equations down here, it proved out that the answer, in other words, what they were getting, they were assuming incorrect things. But if you do this and integrate over the face, it always works. But it turns out that translates exactly back to this pseudo volume. Remove the volume, add the volume, things like that. So, anyway, I think we got 5 minutes, so we might just draw it to a close if you're fine with that. I probably would do, I don't know,